On December 27th, 2024, a robotic telescope sitting on a mountainside in Rio Hurtado, Chile, caught a faint point of light moving against the stars that shouldn't have been there. Nobody watching that data stream in real time understood yet what they were looking at. That telescope wasn't some general-purpose observatory that happened to get lucky. It's part of a network called the Asteroid Terrestrial Impact Last Alert System, or ATLAS, funded by NASA specifically to scan the entire visible sky night after night, looking for exactly this kind of object. Fast-moving points of light that don't match the cataloged positions of known asteroids, comets, or stars. ATLAS operates multiple stations positioned around the globe precisely so that between them they can cover as much sky as possible as often as possible, catching objects while there's still enough time to react if one turns out to matter. According to NASA's own records, 2024 YR4 happened to be bright enough to detect that night specifically because it had just made a relatively close pass by Earth 2 days earlier on December 25th. Meaning the very same close approach that first exposed it to detection was also the reason it was worth watching at all, a small coincidence of timing that ended up shaping the entire year that followed. Within hours of that first detection, the observation was reported to the Minor Planet Center, the internationally recognized clearinghouse that collects and verifies asteroid and comet sightings from observatories all over the world, and from there, the object entered the tracking pipeline that would follow it for the next 14 months, quietly, methodically, long before anyone outside a small circle of researchers had any reason to pay attention. Within 8 weeks, that single point of light would trigger an official global notification from an international network built specifically to warn governments about incoming asteroids. It would become, according to NASA's own words, the highest impact probability the agency had ever recorded for an object of its size. And it would eventually pull in the most powerful space telescope humanity has ever built, not once, but 3 separate times over the following year. Because ground-based telescopes on Earth physically could not answer the question everyone needed answered. This is the real story of asteroid 2024 YR4, and it is the closest thing to an actual documented planetary warning that has happened in your lifetime. I want to be upfront about something before we go further, the same way I always am, because this story has been badly mangled online. The dramatic part of this, the part where the world was genuinely on alert, happened mostly in January and February of 2025. What's just happened, as recently as this year, is the final chapter. James Webb Space Telescope observations that definitively close the case in early 2026. So if you've seen headlines implying Webb just discovered some brand new threat out of nowhere, that's not accurate. What actually happened is arguably more interesting than a fake cliffhanger because it's a complete story with a beginning, a genuine scare, and a real verifiable ending. And Webb was the instrument that both deepened the scare and ultimately ended it. Let's start with what actually makes an asteroid warning official, because most people have never heard of the system that exists for exactly this purpose. When an object is discovered with any measurable chance of hitting Earth, its data gets fed into monitoring systems run by NASA's Center for Near-Earth Object Studies, known as CNEOS, alongside independent European systems. These systems calculate what's called an impact probability, essentially running the object's trajectory forward through every plausible version of its orbit, given the uncertainty in the measurements, and checking how many of those possible paths intersect with Earth. If that probability crosses a certain threshold, an organization called the International Asteroid-Warning Network, or IAWN, issues something that genuinely deserves to be called a warning, a formal international notification that a real, quantifiable, if still small, risk exists. This isn't a headline written to get clicks. It's a specific bureaucratic and scientific process with defined trigger points, built after decades of work by planetary defense scientists, precisely so the world has an actual system for this, instead of just internet panic. And in January 2025, weeks after that Chilean telescope first spotted 2024 YR4, this exact system activated. According to NASA's own CNEOS reporting, once the impact probability for 2024 YR4 crossed the 1% threshold, IAWN issued its official notification. That's the real warning at the center of this story. It happened. It was real. And almost nobody outside the space community noticed it happening in real time. What made scientists especially confident in the numbers behind that warning is that they weren't relying on a single calculation from a single team. 3 independent impact monitoring systems tracked 2024 YR4 in parallel throughout this entire episode. NASA's own Sentry system, a European system called Aegis, and a third called NEODIS, run by a separate group of researchers. Each system takes the same raw tracking data and runs its own independent orbital simulations, specifically so that no single piece of software, or any one team's assumptions, can produce a false alarm or a false all clear on its own. According to a detailed technical account of the episode later published in the scientific literature, all three systems tracked 2024 YR4's impact probability in close agreement with one another throughout the entire event, rising and falling together as new data came in, which is exactly the kind of cross-verification that gives a warning like this genuine scientific weight, rather than it resting on one lab's number alone. And it's the same basic principle that lets independent labs replicate each other's results in any serious scientific field. To understand how seriously scientists were taking this, you need to understand a tool called the Torino scale, which ranks the danger of a newly discovered asteroid from 0 to 10. 0 means no hazard at all, the overwhelming majority of objects ever discovered. A rating of 10 means a certain global catastrophe level impact, something that has never once been assigned to a real object in the history of the scale, and hopefully never will be. Almost every near-Earth asteroid ever tracked sits permanently at 0. In late January 2025, as more observations came in, 2024 YR4 was assigned a rating of 3. To put that in perspective, according to multiple space science outlets tracking the story, only one other object in the history of the Torino scale has ever been rated higher, the asteroid Apophis, briefly rated a 4 back in 2004, before follow-up observations ruled out any danger from it as well. For about a month, in early 2025, 2024 YR4 was the single highest-rated threat ever tracked by the world's asteroid monitoring systems, while the danger was still considered live. Every other object being tracked anywhere on Earth sat at 0. This one didn't, and for the handful of scientists watching the number climb in real time, that fact alone made 2024 YR4 impossible to treat as routine. The Apophis comparison is worth sitting with for a moment because it's the closest historical precedent this situation had. When Apophis was first discovered in 2004, its initial impact probability for a potential 2029 collision was calculated at roughly 7%, briefly making it the highest-rated object the Torino scale had ever recorded. It took targeted radar observations over the following year to finally rule out any danger, at which point Apophis was downgraded all the way back to 0. That entire episode became something of a case study in planetary defense circles for exactly how these scares tend to play out. A real, non-trivial early estimate, followed by growing precision, followed eventually by relief. Scientists watching 2024 YR4 climb toward and past that same Torino level in early 2025 were, in a very real sense, watching the second ever instance of this exact scenario play out in front of them, one only slightly less alarming on paper than the one that had defined the field 2 decades earlier. Here's where the story gets genuinely tense, and this part is not exaggerated at all. It's documented, published, and easy to verify. When 2024 YR4 was first discovered, its estimated chance of striking Earth on December 22nd, 2032 was calculated at around 3%. That's already unusually high for a newly found object. But over the following weeks, as more observatories around the world reported additional tracking data, that number didn't fall the way most initial asteroid scares eventually do. It climbed. Multiple independent sources documented the sequence. 1, 3%, then 1, 8, then 2, 2, then a jump to 3. 1% by mid-February, a number NASA itself described, according to reporting from that period, as the highest impact probability the agency had ever recorded for an object of this size, or larger. At that same time, scientists estimated the asteroid itself was somewhere between 40 and 90 meters across, roughly the height of the Leaning Tower of Pisa, or a 10-story building. Not large enough to be a global extinction-level threat, but plenty large enough to level a city if it struck a populated area, based on published impact hazard modeling for objects in that size range. Now, if you've never followed a story like this before, that rising number probably sounds like the situation was getting worse and worse in a straight line. It wasn't, and understanding why is actually the key to understanding how this entire system works, and why headlines about asteroid risk are so often misleading. When an asteroid is first discovered, astronomers only have a short arc of observations to work with, which means there's a wide range of uncertainty about its exact future path. Imagine a narrow cone spreading outward from today into the year 2032, representing every physically possible trajectory given the current data. Early on, Earth might sit only at the very edge of that cone, giving a low probability. As more observations arrive and the cone gradually narrows, if Earth happens to still be inside that shrinking range, the probability can actually climb, because the same total chance of impact is now being concentrated into a smaller area that still contains our planet. That's exactly what was happening through January and February 2025. It wasn't that the danger was truly increasing, it was that scientists were getting a sharper and sharper picture of a narrowing set of possibilities. And for weeks, Earth kept stubbornly sitting inside that narrowing zone. A simpler way to picture it, imagine someone throwing a dart at a wall from across a room, but you can only see roughly where it's going to land, not the exact spot. At first, your best guess covers a huge circle on the wall, and Earth's bullseye takes up only a small fraction of that circle, so the odds look low. As you get better information about the throw, your circle of uncertainty shrinks. If the bullseye happens to still be somewhere inside that shrinking circle, your calculated odds of a hit actually go up with every improvement in your information, right up until the moment the circle either shrinks down around the bullseye, confirming a hit, or shrinks down and drifts entirely clear of it, confirming a miss. There is no in-between resting point where the number just stays flat. It either keeps climbing toward 1 or it eventually collapses towards 0, and there's no way to know in advance which one you'll get until the data itself decides it. That is precisely the mechanism that took 2024 YR4 from 3% to 3, 1% in a matter of weeks, and it's also precisely the mechanism that let it collapse to near 0 within days after that peak. The real turning point, the moment that determines whether a story like this ends in relief or continued alarm, is what happens when that cone finally narrows enough to reveal whether Earth is inside it or not. For 2024 YR4, that moment arrived within days of hitting its peak. On February 23, 2025, new observations allowed CNEOS to update the calculation again, and this time the shrinking uncertainty region had moved. Earth was no longer inside it. According to NASA's own announcement, the Earth impact probability for 2032 fell essentially to near 0. And by the following week, official NASA statements described the risk to Earth as effectively eliminated for the foreseeable future, later refined to a formal figure of just 0.004%, with no significant potential for impact for the next 100 years. On paper, this should have been the entire end of the story. A tense, genuine, internationally recognized warning that resolved exactly the way the system is designed to let it resolve. Through more data, not less panic. Except it wasn't quite the end, because a second, much stranger thread had opened up in the middle of all this, and it's the thread that eventually pulled James Webb directly into the story. Even as the Earth impact risk collapsed to nothing, scientists noticed that the range of possible locations for 2024 YR4 on that same date, in December 2032, still included a small but real chance of striking something else entirely. The Moon. This wasn't a typo or an afterthought. It became its own tracked figure, published and updated independently from the Earth risk. As of May 2025, NASA reported the lunar impact probability at 8%, and by June, additional data pushed it up again to 3%. If you're keeping score, that's a higher percentage than the Earth impact odds ever reached at their absolute peak. For most of 2025, there was a genuinely open, unresolved, single-digit % chance that a building-sized asteroid was going to hit our own moon in December 2032. And nobody could yet rule it out. It's worth pausing on why a lunar impact, even though it posed no direct danger to anyone on Earth, was still being tracked this seriously. NASA's own statements on the subject were clear that an impact of this size would not meaningfully alter the moon's orbit. The moon has absorbed far larger impacts throughout its history and will absorb more in the future, without any noticeable change to its path around Earth. But that doesn't mean scientists considered it a non-event worth ignoring. An impact of this scale, striking at roughly 57 kilometers per second relative velocity, would carve out a fresh, visible crater, and would very likely produce a bright flash of light, potentially visible from Earth with the naked eye or through a basic telescope, depending on which side of the moon it struck and the exact geometry at the time. There was also a more practical concern raised in the scientific literature. An impact event of that size could throw a meaningful quantity of lunar debris into space, some of which could plausibly reach altitudes relevant to Earth-orbiting satellites, and, in the most extreme modeled scenarios, even cross paths with Earth itself over subsequent years. None of that made the lunar scenario dangerous in the way the original Earth impact scenario was, but it was real enough and specific enough that it stayed on the official tracking sheets for over a year, refusing to resolve, right up until Webb's final observations closed it out for good. This is exactly the kind of problem James Webb Space Telescope exists to solve. And it's worth explaining why, because it's not just a better camera. Ground-based telescopes track an asteroid like 2024 YR4 using visible light, essentially watching how much sunlight it reflects. But reflected brightness alone can't tell you an object's true size, because a small, highly reflective rock and a larger, darker one can look identical in visible light. To actually pin down the physical size, you need to measure the asteroid's own heat, the faint infrared glow every object gives off, because that heat signature depends on physical size in a much more direct, reliable way. That kind of precision infrared measurement for an object this faint and this far away is something only an instrument like Webb can realistically do. Think about it this way. Two rocks sitting in direct sunlight, one pale gray, one nearly black, can reflect wildly different amounts of visible light, even if they're the exact same size, simply because one surface bounces sunlight back more efficiently than the other. A telescope watching only reflected light has no reliable way to tell the difference between small and shiny and large and dark. Both can produce the exact same brightness reading from Earth. But heat works differently. Both rocks absorb roughly the same fraction of the sunlight hitting them regardless of color, and both re-radiate that absorbed energy as infrared heat in a way that scales far more predictably with actual physical size. That's precisely why NASA cleared special observing time on Webb specifically for this purpose, using its infrared instruments. Not because it takes prettier pictures, but because it was, quite literally, the only telescope capable of resolving the one physical property, true size, that ground-based visible light surveys structurally could not measure with any confidence. In March 2025, Webb's results came back. The asteroid's size was refined down to a range of 174 to 220 feet, or roughly 53 to 67 meters, about the size of a 10-story building, and notably narrower than the original ground-based estimate, which had ranged all the way from 40 to 90 meters. That's not a small clarification. That kind of size range directly changes the modeled damage radius if the object ever did strike a populated area, which is why nailing it down mattered enormously to the scientists running these risk calculations, even after Earth itself was no longer in danger. Then, through the rest of 2025, something inconvenient happened from a tracking standpoint. 2024 YR4 kept moving further from Earth along its orbit, eventually becoming too faint and too distant for ground-based telescopes to see at all. Normally, that would mean waiting, essentially blind, until the asteroid swings back into view. And according to NASA's own scientists working the case, that wait wouldn't have ended until 2028, leaving years of unresolved uncertainty hanging over that lingering lunar impact question. Instead, the team went back to Webb a second and then a third time, using what's called Director's Discretionary Time, an emergency allocation reserved for exactly this kind of urgent, time-sensitive science that can't wait for the normal competitive scheduling process. Webb observed the asteroid again in February 2026, capturing what NASA described as among the faintest direct detections of an asteroid ever attempted with the telescope, essentially spotting a 10-story building-sized rock at a distance where it had become effectively invisible to every other telescope on or near Earth. And this is the actual, real, current answer to the warning in the story's title. The new Webb data, combined with archival images stretching back before the asteroid was even officially discovered, allowed ISINIOS scientists to extend the observed history of 2024 YR4's orbit from roughly 5 months of tracking data all the way to nearly 2 full years. According to NASA's own reporting released in March 2026, that additional baseline improved the precision of the asteroid's predicted 2032 position by close to 20%. And when scientists plotted where that newly narrowed range actually sat relative to the moon, the answer was clear. Webb's own imaging showed the asteroid sitting measurably offset by about half an arcsecond, roughly 22 pixels in the telescope's raw data, from the position that would have been required for any non-zero lunar impact probability at all. The lunar risk, like the Earth risk a year earlier, dropped to 0. The current best estimate has 2024 YR4, missing the moon by roughly 21,200 kilometers on December 22, 2032. Safely, and with very high confidence, according to results published in the research notes of the American Astronomical Society in early 2026, a formal peer-reviewed record that closes out this specific chapter for good. So if you strip away the misleading framing, here's what James Webb Space Telescope genuinely did, in order. It confirmed the true physical size of an asteroid that had briefly become the highest-rated impact threat ever tracked by modern planetary defense systems. It provided the infrared precision no other instrument on Earth could deliver at a moment when the asteroid was too faint and too distant for anything else to see it at all. And, using emergency observing time granted specifically because the clock was running out before the object vanished from view until 2028, it delivered the final data needed to rule out even the backup, secondary threat to the moon that had been quietly climbing for most of the previous year. That is a genuine warning system working exactly the way it's supposed to, tracking a real threat through its entire life cycle. From first detection to record high risk assessment to full resolution, using the most advanced instrument humanity has ever pointed at the sky, and doing all of it in the open, published in real scientific papers with real names attached, rather than hidden or spun for views. The two scientists who led the Webb observing program that finally closed this case, Andy Rifkin of the Johns Hopkins University Applied Physics Laboratory and Julian DeWitt of MIT, put the stakes plainly in NASA's own release on the results. Without Webb, the team would have had to wait until 2028, carrying a large amount of unresolved uncertainty the entire time before the asteroid became visible again from Earth. With these observations, that uncertainty was simply removed, years ahead of schedule. It's worth taking a step back and putting this in context because a building-sized asteroid isn't some abstract, harmless curiosity. It's precisely the size category that planetary defense scientists worry about most in practical terms. For comparison, the asteroid that exploded over Chelyabinsk, Russia, in 2013, an event that injured over 1,000 people, mostly from shattered glass, and was caught on dashcams around the city, was only about 20 meters across, roughly a third the size of 2024 YR4's confirmed range. An object in the 53 to 67 meter range, striking a populated area, would be capable of leveling a city rather than just blowing out windows across one. That's the actual stake that was on the table in February 2025, for the roughly 4 weeks that this asteroid's risk sat above 1%. Planetary defense researcher Bruce Betts, discussing the case publicly while the risk was still climbing, summed up the mood among most scientists working the problem at the time with a line that stuck with a lot of people who followed the story closely. He wasn't in a panic. That's not a scientist downplaying a real threat for public relations. It's the honest, calibrated reaction of someone who understood exactly how these numbers behave, who had presumably watched similar cases resolved before, and who turned out, once again, to be right. A useful reminder that the loudest voice in a story like this is rarely the most reliable one. It's also exactly why the international system that tracks these objects exists in the first place, and why an agency like NASA maintains a publicly available, constantly updated risk list called Sentry, where anyone can currently check every known asteroid on Earth's radar and its exact odds in real time for themselves. And 2024 YR4 isn't gone from that conversation either. It's still out there, still being tracked, still logged in NASA's official records with its full orbital history documented for future reference. The techniques refined during this specific case, using Webb's infrared sensitivity to nail down size, using emergency observing time to catch a fading target before it disappears, combining fresh data with archival images to stretch an object's tracked history, all of that is now part of the standard playbook for the next object that shows up on the risk list, and there will be a next one. NASA's automated monitoring systems flag new near-Earth objects constantly, most of which quietly resolve to zero risk within days without anyone outside the field ever hearing about them. 2024 YR4 is simply the one that didn't resolve quietly, the one that climbed high enough, fast enough, to trigger the actual global warning system. And it's the one where James Webb Space Telescope ended up doing some of the most difficult, most consequential astronomical detective work of its entire mission, not to discover a threat out of nowhere, but to methodically, rigorously prove, piece by piece, exactly how much danger there wasn't. There's also a broader lesson buried in this case that planetary defense researchers themselves have pointed to directly. In the published technical account of the episode, the same team that tracked 2024 YR4 from discovery through resolution noted that if radar observations had been available within the first week after discovery, a capability that exists for closer, brighter objects but wasn't available for this one, the entire uncertainty could likely have been resolved almost immediately, skipping the tense, multi-week climb toward record-high odds entirely. That's not a criticism of how this case was handled. It's a roadmap for how the next one might be handled faster, with less public uncertainty along the way, assuming the right instruments are pointed in the right direction at the right moment. Every one of these episodes, resolved or not, becomes training data for the system that has to handle the next object, and the one after that, for as long as anyone keeps watching the sky, funded, staffed, and quietly running in the background, whether or not any of it ever makes the news again. So here's what I think is worth sitting with. For about a month in early 2025, the most sophisticated planetary defense network humanity has ever built looked at a real object, calculated a real non-trivial chance that it could strike a populated part of Earth 8 years from now, and issued a real formal international warning about it, and almost none of us knew it was happening while it unfolded. That system worked exactly as it was designed to, quietly, competently, without needing a single exaggerated headline to justify the attention it deserved. The question I'd actually put to you is this: if IEW's system does eventually have to issue a genuine warning about an object that doesn't resolve down to zero, do you think the public reaction would look anything like how calmly the scientific community actually handled this one? Let me know what you think in the comments. And if you want to check the current status of every asteroid NASA is watching right now for yourself, NASA's Sentry Risk List is public, free, and updated continuously.